So here's another question from test 1, and it's 1F, and this is where we add NBS, otherwise known as N-bromo-6-cinnamide, to this is free radical halogenation of an alkane. It looks like an alkene reaction, but it's free radical halogenation, and I'll explain why that is in a second here. So here's the structure of NBS, or N-bromo-6-cinnamide, and what this is pretty much equivalent to is that when you put this in solution and you heat it up, it breaks down essentially and acts as a source of Br2. So your question is, well, why can't we just use Br2? Well, one of the reasons is that Br2 is this dark brown, fuming liquid that's really toxic and really hard to work with, whereas NBS is a nice yellow solid that's easy to weigh out and to manipulate and to add to your reaction. Another reason is that NBS gives us a relatively low concentration of Br2, and that helps the free radical halogenation occur instead of the reaction that you might be wondering of why it's not occurring if this is actually a source of Br2. Why isn't Br just adding to give me this, Br2 adding to give me this dibromide? And so that doesn't happen in this reaction, yay. And part of it is because, once again, we're using NBS, so we have a really low concentration of Br2. And the other reason is we've got peroxides, or we might have heat is another thing that you might see in this reaction like this, and those are telling us that, okay, I'm going to be forming Br radicals, and Br radicals, they don't do this reaction. Instead, what they do is free radical halogenation, which we're going to discuss. Okay, so the first step in the free radical halogenation is we've got to form some halogen free radicals. So recall that we're going to break the bromine-bromine bond, and we're going to form two bromine radicals. Now, that radical that's been formed is going to abstract a hydrogen from our alkene starting material that's going to lead to the most stable radical. And I've drawn in those hydrogens, so we're going to have our electrons moving like this, and that's going to lead to this alkyl radical plus HBr. And you may be asking yourself, why that alkyl radical? Well, remember that this is actually an allylic radical, which means that it is resonance stabilized. And I'm going to draw the other resonance structure. There it is, and if you wanted to add that arrows in for that, you would show them like this. And there's your other resonance structure. Okay, so now that we've formed this radical, we can go on to our next step. Recall this first step here is an initiation step because we're going from a non-radical species to radicals. This next step that we drew is where the bromine radical reacts with the cyclopentene is a propagation step because we're going through a reaction step where we start with some radicals and we also finish up with some radicals. And now we can do step 3 of this reaction, which is also a propagation step, where we will have this allylic radical that we have formed is going to react with another molecule of bromine, and as it does that, it's going to form a carbon-bromine bond and another bromine radical. And there they are. And now remember that this bromine radical can then go on to react with another molecule of cyclopentene, and that continues the chain reaction.